want to know what value component should be placed here to eliminate reactive power from the source. Right, well, all power leaving the source must be being received by the load, so if there's no reactive power leaving the source, there must be no reactive power entering the load. Reactive power is the imaginary component of the complex power, so if there is no reactive power, that means the complex power must be completely real. If the complex power is completely real, then total complex impedance that it is driving must also be completely real. And that's because we have the formulas like S equals the square of the magnitude of the voltage divided by 2 times Z complex conjugate. The square of the magnitude of the voltage is always real. So if we want S to be completely real, then Z, the complex impedance, must be completely real as well. What is the complex impedance that the source is driving? Well, it's this unknown component here in parallel with a 8K2 resistor, and that's in parallel with this rather large 100 Henry inductor. We're running at 100 Hertz, and that's all we need to know. We actually don't need to know how big the voltage is or what the Thevenin impedance is either. What we're interested in is getting this to be completely real. How do you do that? Well, standard formula for 3 impedances in parallel. 1 over the total impedance is 1 over the first impedance plus 1 over the second impedance plus 1 over the third impedance, and we want this to be completely real. Right. Well, if this, maybe that's not immediately obvious. We want ZT to be completely real. But if ZT is going to be completely real, then 1 over ZT is going to be real as well. Because if you take the inverse of a real number, you get another real number. If you take an inverse of a number with an imaginary component, you get another number with an imaginary component. So we need 1 over ZT to be real. That implies that ZT is real. Okay, so this plus this must be real. This is already real, completely real. It's 1 over 8K2. This is completely imaginary. So if the sum is going to be real, then we've got to get rid of that imaginary by cancelling it out with the imaginary component of this. Simplest way to do that, fit a component here which has an equal and opposite impedance to this component here at this frequency. The impedance of an inductor is J omega L, so 1 over Z3 is going to be 1 over J times 2 pi F 100 times L the 100 here. That's omega, 2 pi F. And that is going to have to be equal and opposite to 1 over Z1. Which means that 1 over Z1 needs to be minus that. Well, that, if I turn these things upside down, that would give me that Z1 has got to be minus J times 2 pi times 100 squared. Now, a capacitor does have a impedance which is minus J over omega C. So it has the right sign. It's completely imaginary and it's negative imaginary, which is exactly what I want to cancel out the impedance of this inductance. So that capacitor there, this component here, has got to be a capacitor, and its value is given by this expression here. Omega is just 2 pi times 100 again. So if we take this equation here and simplify it, the minus j's cancel out, bring the c up here. That would be c equals, and bring the 2 pi 100 squared down here, C equals 1 over 4 pi squared 100 cubed. What's that? Cue the calculator. 4 times pi squared times 100 to the power of 3. And take the inverse of that, and the answer is 25.3 nanofarads. So, to get rid of all reactive power means making the load totally real. To make the load totally real, the component we need there is a 25.3 nanofarad capacitor. Right, one more question to do.